Good morning, Year 12s. Unfortunately, I'm not in school today, so I have made a slight change to our plan. Rather than us having a day where we do some practice, look at test questions, we'll move that to tomorrow. And today, you're going to take a look at what is coming next in our unit. I think this is a fairly easy topic that shouldn't take you too long and should give you plenty of time to do some practice. I don't think will bring up a lot of questions. So I think it will be a good one for me to leave you today. So it's this lesson 7, the logistic function. It starts on page 23. We're going to skip the starter for now. I think we need to have that consolidation lesson tomorrow before we try this starter. So have a look at this first of all. You probably want to pause the video and have a read through this question, have a think about it. I would really encourage you to talk about it with the people around you. Hopefully you have had time to do that. So you can see that the graph on the right hand side seems to grow at the beginning. If we look at the first half of it, it seems to be curving upwards, but then at some stage it kind of curves a bit more downwards. Maybe that doesn't quite fit the second half of it so well. It seems to plateau for a bit, but there definitely seems to be a slowing down, and it seems to reach this maximum towards the end. I'm not sure if the world record has been increased since this data goes up to about 2015-ish. So it seems to get to 2 meters 45 and then stop there. And obviously you can talk about what are the things that have made the record increase. We could try and think about reasons why it might have slowed down or sped up if we were trying to discuss this in context. But the key thing is it's got this idea of two different types of change. We've got an increasing rate of change at the beginning, and then we've got a decreasing rate of change at the end. And both of them have this idea of an asymptote. There seems to be an asymptote around 2 meters 45, and then also this lower asymptote at the start. So this is obviously a new type of functions. And of course, based on the name of this lesson, it is called the logistic function. So it is it's used to model situations where there's a restriction on growth. So we often think of things like bacteria growing in a petri dish as being exponential in growth. It just keeps on doubling. But obviously there gets to a point where the petri dish can't sustain any more growth. And the growth starts to slow down. And eventually maybe the bacteria has filled as much space as it can, and the growth actually stops and it reaches a plateau. So that's another example where the logistic function might be quite useful. Okay, so the logistic function has this form, quite a complicated looking equation. We've got a lot of letters in it. So let's take a look. It is linking, the main variable is the t, which you can see up here in the exponent. We then have, let's see, we've got 1, 2, 3, missed that one, 3 parameters that can control the shape of the logistic function. So yeah, there is quite a lot going on with it. It will look, well, you could put this into Desmos yourself. In fact, that would be a good thing. Pop it into Desmos. Desmos will probably ask you to whether you want it to make sliders for L, C, and K. You can do that, and you can look at how playing with them affects the shape. So that's probably a really good thing to do. So I'd encourage you to pause the video and take a look at that. All right, so you have probably found that our exponential function looks something like this. You can obviously make it have different shapes. We've got this asymptote that we talked about. We have another asymptote here. And we've got this idea of it increasing, and then at some point around about here-ish, it changes. So it goes from increasing, curving upwards, to curving more downwards. It's not going down, but the concavity of it changes somewhere around the middle. If time keeps on going, the function doesn't keep going up, it reaches a limit. And this is often called the carrying capacity. So it could be some sort of physical thing like the size of the Petri dish that affects it, or it could be like how much food source there is for a particular species, or how much habitat there is. So it could be something quite a natural physical limit, a carrying capacity for the model. We can also think kind of a little bit analytically for a minute and think about how that links to the function. So let's see what happens as t gets very big. So we're going to put our analytical hats on for a minute. So as t gets very big, that means that whole exponent gets very big. So what we're going to do is we're going to take this function and we're going to look at what happens. What is the effect of making t a really big value? And we're going to kind of work our way out from t in this function and think about how it affects each thing. So if t is really big, that whole exponent is a large negative value. Minus kt is now a very big negative value. Okay, assuming that k is positive. Then next, if that's negative, that's a very large negative, we're going to think now, we're going to go a little bit broader. What does this look like? E to the power of a very large negative number. You can check that on your calculator. You could do e to the power of negative a million if you want. Okay, what you will find is this gets really close to 0. Okay, let's zoom out a little bit more. So if that's 0, well then, if I zoom out more, this whole term becomes 0, doesn't it? 0 times c is still 0. All right, so c e to the minus kt is going to be 0. So if that's 0, well, that whole denominator then is much simpler. It's just 1 plus 0. So in fact, let's just go for the whole thing. F of t is going to approach L over 1 plus 0. Well, that's just L. Okay, so as t goes to a very big number, we've found that the function approaches L. So L must be our carrying capacity. Carrying capacity. All right, so this line is going to be y equals L. All right, you do not need to memorize this formula. You don't need to memorize that L is the carrying capacity. You do need to know that there is such a thing as a carrying capacity. And yeah, it's kind of useful to remember that it is the term at the top. But yeah, we're not going to do loads of graph transformations with this function. Yeah, we are going to keep it fairly simple. Okay, the last little bit then is if t can take negative values, which doesn't always make sense. Yeah, time being negative isn't always a sensible thing. If we work our way backwards, we know that the function will approach 0. Okay, and we could do that in a similar way. Like we could do a similar analysis to show that. But yeah, most of the time, t being less than 0 doesn't really make sense. Okay, there's a little activity for you to do on page 25. This is a little thinking routine called Connect, Extend, Challenge. It is a useful thinking routine for trying to link new knowledge to what we already know to try and help make connections. I think it would be a really good idea if you spend maybe more than 5 minutes trying to respond to those 3 questions on your own, first of all. You don't need to do them in order. And then I'd encourage you to share with as many other people in the classroom as you want to. You could have a whole class discussion about this if you wanted to. So that will be a nice little activity for you to do. And then there's a bit of practice for you to do on page 26. I would encourage you to try all 3 questions. I think you're going to have time for that. If there is more time left, then I would not do anything else from the linearizing functions. I think we should probably look at that together. But if you've got questions that you haven't done from earlier in the booklet, so I'm thinking page 17 and earlier, now's a really good time to try and get up to date. We are going to have an assessment next week, so it's a good time to start making sure you're up to date with homework, and it's just going to make revision a lot easier. So tomorrow we will take a look at finishing off linearizing functions, have some time to do some practice. We'll have some time to look at any questions we've got from the last unit test, and then Friday we'll finish off our unit. Okay, see you tomorrow, Year 12s.